Problem number 22 gives us an object like this. Now I've just drawn the profile of this object. It actually has some depth to it, so if you wanted to draw the depth, the object goes back a ways, like this. And that distance that it goes back is 3 feet. Let me just double check that it is feet. Yep, it is feet. So I've got 3 feet this way, 2 feet that way, and likewise you're going to have something here as well. Let me draw this side first. Alright, so here's our tank. And it's filled with some kind of fuel that weighs 53.1 pounds per cubic foot. So 53.1 pounds per foot cubed. We're going to do the same thing we did with previous ones. We're going to try and set up the integral that would represent how much work it takes to pump fuel to the level of the engine. Now let's see. The engine is approximately 3 feet above the fuel tank. So 3 feet up here. Let's extend this a little bit further. Up here at 0.6 is the height of the engine. We need to pump fuel from the tank to the engine. As with all these, I'll start with a little slice, a horizontal slice that has a dy thickness. This obviously has limits of 0, 0 and 0, 3 here. This one, I'm going to give coordinates of 0 and y. Over here, this is going to have coordinates of 2 and 3. And this has coordinates of 1 and 0. Now I'm going to need that because eventually I'm going to need to figure out the volume of this one slice and then multiply it by the density. So there's our one slice. Volume of one slice. So the volume of one slice, or maybe I should just put the force on one slice and throw in the density. Volume is, now let me be consistent. Force on one slice. Force is going to equal the weight density times the area times the thickness. So let's see, the thickness is dy, but what am I going to do for the area? The area, well, I'm going to have to fuss on that one a little bit. If this has coordinates of 0 and y, what will the coordinates be over here? Or do I not know them? What is it in y? X and y. X and y, because at 1, all right, I know that one, I know this one, but I don't know the stuff in between. So we'll just call it x and y. So the weight density is going to be the area times the thickness. So, the force is going to be the weight density times the area times the thickness. So 53.1. Now what kind of a figure am I going to get when I take a cross section horizontally? A rectangle. So a rectangle is going to be the width times the length. Width times the length. Now at least one of these is pretty easy, right? That's going to be 3 feet. So that part we got. Let's call that the length. But what about the width? How far is that? 53.1. Well, x minus 0. So just a distance of x times 3 times dy. But there's a problem here. The problem is this is in terms of x, but our integral has to be in terms of y. So what we need to do is we need to find the equation of this line right here. So that line. What's the equation of that line? Well, you can figure out the slope of this line, right? If you move over 1, you go up 3. So the slope is 3. And once you have the slope, it's y minus y1 equals m times x minus x1. The point that I would choose to plug in here, and you could plug in either of these, but I'd plug in the 1 and 0. So if you plug in the 1 and 0 into this, let's see what happens. We get y minus 0 equals 3 times x minus 1, or better yet, y equals 3x minus 3. But that's x or y in terms of x. We want x in terms of y. If you solve for y, if you solve for x, I should say, you get y plus 3 divided by 3 equals x. So I'm going to take that expression and plug it in here. I get 53.1 times y plus 3 over 3 times 3 dy. We run into something a little bit nice here. What's that little something nice here? Yeah, that's special. 3 cancels out. So the author's doing something nice for us. That's good. So we end up with 53.1 times y plus 3 dy. And that's the force of moving, required to move one slice. That's just the force. Now, how far do I have to move it? In other words, what's the distance that that slice moves? Anyone? Not quite 6 minus 0. Oops. It's going to be this distance right here. 6 minus what? 6 minus y. So distance is going to be 6 minus y. Here's our force. Distance is 6 minus y. So overall, the work done to move just one slice is going to be the product of these two things. So it's going to be 53.1 times y plus 3, and I'll change the order up here just for convenience, times 6 minus y dy. And that's just to move one slice. Now, if we're going to pump out all the gas from this, then that gives me my limits of integration. Now keep in mind, you have to stay within your figure. And our figure is right here. Here, 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 here. So, if I'm going to pump this completely empty, what should be my limits of integration? 0 to 3. So the integral from 0 to 3, 53.1 y plus 3 times 6 minus y dy. And from there, what I would do is just FOIL it all out, or just dump it into numerical integration. What you should end up with is 1035.45 foot-pounds. Yes, sir. Yeah, so yeah, it is going to be based on the slice. The reason we had to do a little extra work here is because the slice is going to change depending on how high you take it. So in some other problems that we've done, like problem number 18, doesn't matter where you take the slice, it's still going to be a circle of the same radius. But here it changes. In problem number 19, it changed. So if that area changes, then you're going to have a function that reflects its changing area based on the height. And so that's what made problem 19 harder than problem 15. This, you have a uniform area independent of where you take your slice. So, yeah, good question. Thank you. Anything else on problem number 22 here? Yes, sir. Oh, so the engine is a distance of 3 feet above the top of the tank. So you're pumping that gas up to that height. So the distance is going to be the difference between this height and your value of y. So 6 minus y. That's going to be the distance.
You know, with that angle at the bottom, the angle on the right-hand side, you would think you wouldn't have enough volume from 0 to 3 to pump from 3 to 6. Because of your red angle?
This one here. I would. Yeah, I see what you're saying. You know, I would assume that they would put the intake here, someplace, and then have it pumped up there. But you're still going to be doing the same work. I mean, there's some things about that kind of bother me, but you are still. The net effect is that this is going to get transferred up to this height. Let me give you some homework. For homework, this is section 7.5. Homework, try 1 through 19. And let me just take a look at a couple more here because I want to delete some chain ones. You know what? Tell you what. Let's do just 1 through 23. And that'll be it. 1 through 23. So I threw out a few problems like moving chains, etc. Whew. Okay. Almost done. One more section to go. Save the best for last. Yay. No rest for the wicked. Quick joke here for you. And we ran across this one earlier. It had to do with this one. What happens when you integrate e to the u? What do you get? Yeah, you get e to the u. You get the same thing back, e to the u. So, the joke goes like this. There's a function party. And tangent, and cosine, cosecant, x squared, square root of x, log of x, they're all hanging out. Except off in the corner is e to the x. And they start to get a little worried about him. They go over to him and say, hey, e to the x, why don't you come join us, hang out. And e to the x kind of shuffles around, looks at the ground a little bit, and goes, I don't know. Every time I try to integrate myself, nothing changes. All right, so math jokes. If you understand them, you probably don't have any friends, right? All right, let's move into section 7.6, our last section for today. We're going to try and find centers of mass, basically a balancing point for different objects. Now, throughout this section, we're going to assume we have something called a planar lamina. And what that is it's a very thin object of uniform density. So it has some small thickness and it's uniformly dense throughout. So to find your center of mass, we're going to try and look at a couple things and balance them. Figure out what's the rotational force that tends to move things around this way. What's the rotational force that tends to move things around the y-axis? So, or the x-axis, and then of course the y-axis. Now, let me demonstrate this in kind of a finite case, a nice simple case that we can do without calculus. And we're going to give this object, this is on your handout by the way, coordinates here in the corner of 0, 0. And of course up here we'd have coordinates of 0 and 3, 2 and 4, and this would be the point 4 and 2, and so on. Let's first of all figure out the total area of this object. I'm going to do that by kind of cutting it into a couple different rectangles. So I don't think that's too hard, right? Let's start with the area of A1. What's the area here? 3 times 1, 3. Area of the second one, 2. Area of the third one, 2 again. So total area for this object of 7. And you're getting kind of a fast treatment on this stuff. And I apologize up front. Hopefully the handout will help out in terms of easing some of our burden. Let's figure out where the center is for each of these. Where's the center? If you had to balance A1, where would you put your finger? Underneath what point? Well, 1/2. And what else? Yeah, 1.5. So let's call it 3/2. Now let's do the same thing for A2. Let's find its center point. So 2 and what else? 1/2. And last but not least, let's find the center point for A3. And what's that going to be? Thank you, 7/2 and 1. Now, you can use 3.5 or 0.5, those kind of things. That's fine. I just tend to like to use fractions, etc. Now we're going to try and find where you'd have to put your finger in order to balance the entire object. I'll give you a little heads up. It may be that the center point is not actually on this object. It may be that you can't physically find a point that will balance it, but we'll see. All right, so what we're going to do is we're going to find two things. We're going to find the force that would tend to rotate this around first the y-axis. So what would that rotational force be? Well, that rotational force is going to be a product of a couple things. It's going to be a product of where that force is felt, which is at 1/2 along the x-coordinate, times the mass of this, which is going to be proportional to the area, or 3. So 3 times 1/2, that's the force that wants to drive this and turn this around the line x equals 0, the y-axis. Likewise over here, at this point 2, you've got a force of 2, that's the area, that wants to rotate it around the y-axis. And you add these things up, the product of the distance away from its axis of rotation, 1/2, times its mass. 2, that distance, times its mass. And then 7/2, that's that last distance, times its mass. When we divide that by 7, we end up with a total of 25 over 2 divided by 7. And that's our, so we call x bar. That's going to be 25 over 14. About 1.78. Let's see if we can't do that same thing for rotating around the x-axis. See if we can't set up the same kind of thing. And what we want to do is we want to figure out, well, what's the tendency of this to want to rotate around the x-axis? Well, that's going to be the place where our force can be localized and felt, which is right here, times the distance to the x-axis. So I know that the area of this is 3. But what am I going to multiply it by? Somebody said it. By 3/2, right? Because it's going to be 3/2 is that distance to your x-axis of rotation, times the area of that little plate. Try and do the next 2. Try and figure out the rotational force around the x-axis. So Vang, what should I put here for the next one? All right, so 1/2 times what? 2. Because that rotational force is going to be felt right here at a height of 1/2 above the x-axis times this area, which is 2. Good. And back. Yes. What's the last one here, please? All right, 1 by 2. Good. And if you multiply this all out, you end up with 15/2 divided by 7, which is 15/14. So about 1.07. Now, if you look, this point, our center of mass, actually isn't on our figure. 1.78, 1.07. So 1.78 is about here, and 1.07 is a little bit above. So it doesn't actually fit there. Bummer. All right, but that's the kind of calculation we're going to be doing in finding center of mass when our figures aren't nice and block-like like this. When our figures start to vary in terms of their height and width, depending on where you're at along the x or y axis. So we're going to be doing the same thing again, except with these types of figures. Again, we're assuming a planar lamina, something of constant density, thin material. Now, this is how we're going to work things in general. We're going to first start by figuring out the mass of your planar lamina. I'm assuming that that material has a density of rho. We're not going to pay too much attention to that because rho is eventually going to divide out, so I'm not going to worry about it too much. But the first calculation is going to mimic what we did up here. We're going to find the total area. So that total area is just going to be the distance between two curves integrated over A to B. So that's where we're going to start. That's the total mass of your lamina. Then you're going to find the moment around the x-axis. That's going to be the tendency of this to want to rotate around the x-axis. So let's see if we can't come up with an expression for that. It's going to start like a lot of our things do with a little slice through your region. What's the thickness of that slice? dx. So that's going to tell us that we're going to set up all of our work in terms of dx. So the tendency for this to want to rotate around the x-axis, so around here, is going to be where that force is felt times the distance to your axis of rotation. So where that force is felt is a little bit challenging. The distance to the axis of rotation, let's see, it's going to be where that force is felt. So it's going to be the midpoint of this times the area of one slice. So my apologies, I misstated that a little bit. This area times this distance. Now this area right here is going to be dx times the midpoint of that slice. The midpoint of a slice is going to be f of x plus g of x divided by 2. So that's the height. That's where this is going to be feeling its rotational force around the axis. That distance times the area. Well, the area is just going to be the top minus the bottom times the thickness, which is going to be our dx. So f of x minus g of x times dx. That's going to be your moment around the x-axis. We're going to repeat that calculation for the moment around the y-axis. At least around the y-axis, things get a little bit easier. We're still going to try and figure out the rotational force of this slice as it tries to rotate around the y-axis. But one part of our calculation got a little bit easier. And that is the distance over which that slice operates. The distance from the y-axis to here is just x. So it's going to be x times this area again. So that area we just dealt with up above is f of x minus g of x. That's going to give you the moment around the y-axis. Your center of mass then is just a couple ratios. The coordinates of your center of mass are going to be the moment around the y-axis divided by m. That gives you your x-coordinate, and vice versa for the y-coordinate. So, kind of involved, but let's do a couple examples to try and help you out. We'll start with problem number 20. And the good news for us, I think I got number 20 on your handout, don't I? Yes. Back to the front page. Problem number 20. So we want to figure out, for this figure, what would be your balance point? Where would you put your finger to hold it up? Well, we'll find out. We're going to start by cutting a slice through this figure in the dx direction. So one slice just like that. Actually, you know what? Before I even do that, I should probably figure out the area of this curve. So let me give you a couple labels here. The top curve is y equals the square root of x plus 1. The bottom curve is y equals 1/3 x plus 1. Based on your drawing that you're given here, I think you can see where these two figures intersect each other. They intersect at 0 and up here at 9. If you were stuck at home, though, how could you figure out where these two things intersect? Yeah, use your calculator, graph them there. Nothing wrong with that one. Or, yeah, set them equal to each other and solve. All right, the ones will cancel each other out, square it, solve, etc. You get solutions of 0 and 9. Okay, our first goal then is to find the area between these two curves. So let's do that. So this is a good review from section 7.1. We're going to integrate from 0 to 9, top minus bottom. So the top curve is square root of x plus 1 minus 1/3 x plus 1 again dx. You get some cancellation. It's going to be the integral from 0 to 9 of x to the 1/2 minus 1/3 x dx. Do I have to go through all the details on that? No. Good. I was really hoping you wouldn't make me do that. You're going to get 9 halves. All right. So that's the mass of this, or that's the area times whatever density that is. That would give you the mass of this little planar lamina. The next thing we have to figure out is the moment around the x-axis. Or you can do the moment around the y-axis. It doesn't matter. So that's the tendency of this little strip to want to rotate around the line y equals 0, around the x-axis. Sounded like it's shatterproof, so probably okay, right? Wow, do you have to register that with the police? Oh, okay. All right, that's good. So let's try and understand the force that this tries to rotate around the axis with. It's going to be a product of two things. One of those things is the area of this little piece. Now the area of that piece is going to be the thickness times the height. So what's the height of that little figure? Well, you can do it in terms of y's. You call this y1 and y2. It's going to be y2 minus, or y1 minus y2 is the height. But then you're going to multiply that height times a dx. So I probably don't want y2 minus y1. I want to do it in terms of x's, right? So let's see. I want the area of that slice. So the area is going to be really just this right here. The difference between those two, which is this. In fact, this is perfect right here. That little bit right there is the area of that one slice. So let me put that in here. X to the 1/2 minus 1/3 x dx. That's the area of one slice. Right there. The other thing I need to know is the distance from the center of this, which is where you can imagine all that force being felt, to the x-axis. So what's that distance? Well, y minus 0, yeah, I mean, that kind of works, but we're eventually going to need to write it in terms of dx. So what's going on is that this point is the midpoint of those two curves, right? Now when you're finding the middle of something, how do you find the middle of two numbers? You average them. You find the mean. So let's average these things, right? So what you're going to have to do is average this function and this function. So it's going to be the square root of x plus 1 plus 1/3 x plus 1 divided by 2. So you're just averaging those things. This one gets really messy, which is probably an understatement. Let's come back to this one in a little while. The important thing is that you get the setup here. So area of one slice, and then this is the distance to the x-axis. Distance to the x-axis. Let's repeat this calculation for the moment around the y-axis, m sub y. And that one's going to be a little bit easier. Oh, one thing I'm missing here. What is it? Limits of integration. What should the limits of integration be? Since we're integrating with respect to x, 0 to 9. 0 to 9. So anywhere that you can imagine this slice being taken and still be within the two curves. So 0 to 9 here. Let's repeat our calculation here. This time we're trying to find the tendency of this little slice here to want to rotate itself around the y-axis. So I'm going to need something new and then something not so new. I need the area of this figure. Well, I've got that. The area of that figure is just going to be this part right here. But I also need to know this distance. Now for your dx terms, don't imagine them as having any real thickness. Dx is arbitrarily small. So we just need to characterize this distance. That distance is just x. So the distance to the y-axis is just x. Distance to the y-axis. So it's just x, again, times the area of that slice. And the area of that slice is going to be the square root of x minus 1/3 x times dx. Here's a good place where numerical integration can really save us a lot of work. All right. The important thing is being able to do the setup. Now, I did grind it all out. Let's see here. My turns out to be 81 over 5. Mx turned out to be 15. And let's put that all together to find the actual center of mass and see if we get something that makes sense. Now, for an object like this, you know, would you expect a center of mass like over here? No. So, I mean, there's limits to what we would expect for our center of mass. For a figure like this, it's probably going to be on the figure itself. It's only when you get things that are not nice and neatly connected that you might have something off of your actual planar lamina for the center. But let's see if we can't finish this up then. So for our center of mass, remember x bar is going to be my over m. So that's going to be 81 over 5 divided by 9 halves. Invert and multiply. So 81 over 5 times 2 over 9. So 18 over 5, or about 3.6. For y bar, it's going to be m sub x, moment around the x-axis, divided by m. So 15 divided by 9 halves, and that's going to simplify 15 over 1 times 2 over 9, 30 over 9, 10, let's see, 10 thirds. Okay, so 3.6, 3.33, 3 bar, call it that. What gets long here is foiling this out and then doing the integration. Yeah, no, I understand it's long and tedious. There are some tricks here that you can play. Trying to think. The one that you can play, if you're pretty good, is this one down here, and that is, if you actually have this formula memorized. I tend not to memorize these formulas. But if you factor out the 1/2, what you're left with, and let me just write it without the x's, f plus g times f minus g, and leave the 1/2 out in front here. Does anyone recognize what happens when you multiply these two binomials together? F squared minus g squared. So that can save you a little bit of work depending on the particular problem. I'm just not a big fan of memorizing things. I think I've shown you several times, even tonight, how to avoid memorizing things. Like, don't memorize all the different forms of the Pythagorean theorem. Just come up with what you need when you need it. So, something bothering me about this one still. You know what? I think, I'm sorry, m sub x, it's not 15, it's 45 over 4. So if I change that, 45, let's see, yeah, 45 over 4, 45 over 4. Let's see what that does to our calculation then. That's going to go in there 5 times. I'll end up with 5 halves. That looks a little bit better. So 3.6 and 2.5. If we look at our figure, that point is plotted on your figure for you, so you can kind of see where it would be. 3.6, excuse me, 2.5, and then 3.6. Other way around. I was right the first time. 3.6, 2.5. And that looks reasonable for its point of balance. One last one here, and I think our figure is going to be a little bit easier to work with. Here, 11, 12. so this one's not explicitly in the book. So let me just give this one to you this way. We're going to look at a figure bound by x equals 2y minus y squared and x equals 0. The problem that you're going to run into with something like this is that unless you're using Desmos or something similar, you're not going to be able to graph it. You can switch things up and try and use your imagination a little bit, but let's figure out what this graph is going to look like. If I switch this around, this is minus y squared plus 2y. What do I know about this? Well, because of the y squared, it's a parabola, right? Because of the fact that it's in y squared, it's going to open left or right. It opens to the left because you've got a minus here. Let's factor out the negative y. So it's negative y times y minus 2, like that. And now I can kind of see where this graph is going to cross the y-axis. You're going to cross the y-axis when x equals 0. So, what values of y will make this product 0? 0 and 2 for y. So 0 and 2 for y. So basically, I've got something that looks like this. So it crosses here at 0, 2, and here at 0, 0. The other thing that bounds my graph is the line x equals 0. So I want to find the center of mass for something like this. And this one's going to work out a little bit nicer. Now, I'm going to start by taking a slice perpendicular to my axis of rotation, just like I did in the last one. What's the thickness of this slice? dy. If I want to find, first of all, the total area here, certainly I don't want to take a dx slice because dx slice would go from the curve to itself. But the dy slice works out pretty good. So let's take that dy slice, and I'm going to integrate this little piece. Let's see if I can't find the area of that one. This has coordinates of x and y. This distance here is x minus 0, or excuse me, this area is x minus 0, or just x times dy. So area equals x times dy. That doesn't work too good. You're not going to have x and dy in the same thing. But here we go. X is 2y minus y squared dy. So that's the area of one slice. 2y minus y squared dy. If I need to add up the area of all such possible slices, I can do that with integration. Where am I going to integrate between 0 and 2? And if you take the time to do that all out, you'll end up with 4/3. And because the integration part's not the essential part here, I'm going to skip that part. Let's work on a couple of our moments. So we'll start with the moment around x, m sub x. This is going to be the tendency of this figure to want to rotate around the x-axis. So this one right here. Now that tendency is going to be a product of two things. It's going to be a product of the area of that slice times the distance to the x-axis. So integral, we're going to integrate where you can integrate here, so from 0 to 2. And it's going to be the area of that slice times the distance to the axis of rotation. Am I still recording my sound here? Playback voices, yes. Okay, thanks. Is that what you're... Volume column? I think I still got some volume here. It might be my playback. It's the speakers. Yeah, so we're okay. So I want this distance to the x-axis times the area. It's going to be the integral from 0 to 2. This distance is the easier of the two. That distance is just y. Now how about the area of that slice? How can I calculate the area of this slice? Well, I've already did. It's that part right there. It's the width, or the height here, times the thickness. So it's going to be 2y minus y squared dy. Might want to go back and double check this. Mimi, can you do this one numerically or something like that real quick? Double check that on that. We're going to work on m sub y. M sub y is going to be the tendency of this figure to want to rotate itself around the y-axis. So how hard is this pushing down, and from how far out? So let's start out with the how hard is this pushing down. That's just the area of this. Okay, so the area of that is going to be the same thing as here. So I want the distance to the y-axis times the area again. And that area is going to be this part right up here. This is going to be the integral from 0 to 2 times 2y minus y squared dy. That's my area again. So we've got the area creeping up twice. Right here, and again here. The only thing left to characterize is the distance from here to the from here to the y-axis. That distance is going to be the midpoint of this little slice. Now, fortunately for us and Sandra, that midpoint is going to be a little bit easier than the last one. All right, and the reason for that is because one of our functions is 0. So basically, it's just going to be this plus this divided by 2, or this plus this divided by 2. So 2y minus y squared plus 0 divided by 2. The 2, that's a factor that can come out in front. Yeah, basically you end up squaring this thing, right? Yeah, that's all right. So 1/2 the integral from 0 to 2 of 2y minus y squared dy. squared. Again, I'm going to kind of blow through a few calculations here for us. M sub y is going to be 8 over 15. And m sub x turned out to be 4/3. So I think I've got everything I need now to find the center of mass. X bar and y bar are going to be m sub y divided by m and m sub x divided by m. M sub y, let's see, 8/15 divided by 4/3 and 4/3 divided by 4/3. At least the y coordinate makes sense, right? Remember what we're trying to find here. Trying to find the point where things balance. And that's going to balance, at least in the y direction, at 1. And in the x direction, what? Yeah, in this one they happen to be the same number, which is interesting. But let's understand the reason for it. If you look at this, in the y direction, if you're going to find a balancing point, it'd be right here in the center, right? And right here in the center is your height of y equals 1. That's your break-even point. All right, that's the middle of this. And that's what our calculation showed us. Is right in the center, that's where we're going to balance it. Now, in the x direction, it's probably not going to be right in the center here. It's probably going to be a little bit closer to here than it is out to here, because there's more mass closer to this. I don't know. Maybe my figure's not good enough that I can tell. Let's see. 8/15, invert and multiply. 3 will cancel. I'll put a 5 there. That cancels in there. 2/5. 2/5. So yeah, it is a little bit closer to the y-axis than it is to its vertex. But no, that's the exact point. That's the exact point where you would locate something to balance it. So right there. In hindsight, you probably didn't have to do things in the y direction because you can kind of see that, all right, this is a nice symmetric figure. Its balancing point has to be along this axis of symmetry. But in the x direction, we didn't know. For homework, just double check a couple of these. You know what? We're going to skip the 1 through 7 part. Let me just give you 13 through 25. So that's what? 1, 2, 3, 4, 5, 6, 7, 8. 8 problems. And I promise not to put any more than 8 problems on the exam like this, okay? All right. Have a good week. See ya.